Yeah, as you can see here from the title, it is about the magnetotelluric, and please note that I have put a dash between magneto and tellurics because I was in a webinar the other day, and there was a discussion about how to pronounce magnetotellurics. So I've decided, okay, to split it and not to look like one of these long German words that you cannot pronounce. So it is about a magnetotelluric, and throughout the talk I will use the abbreviation MT whenever it is appropriate. And yeah, I will go over some theoretical background and show some exciting examples from deep applications as well as near surface application. So for those who may leave early and don't get to the conclusion, one of the main conclusion point is MT is great. So you can leave now if you are not interested to know why it is great. So to justify this conclusion point, why MT is a good method, I will give a quick introduction into MT. I hope that it will not take more than 10 to 12 minutes. I will touch the basis, of course. Before we go in a journey around the world and show you several examples to explore the lower crust, uppermost mantle, as well as crustal studies, and going a little bit shallower and show uppermost crust for geothermal and mineral exploration specifically, also from different places from around the world. Of course, with regard to mineral exploration, as Stephanie said, there will be another talk given by Alan Jones, who will show and discuss more, of course, examples. Yeah, magnetotelluric, it is one of the EM methods in geophysics, and unlike the other methods like transient EM method or DC geoelectric methods, let me see if that works. Yeah, transient electromagnetic DC geoelectric or control source EM method, in which usually we use a man-made source, or let us say an active source. So we inject some energy in the subsurface and we measure the responses. The MT method is different in that way. We don't use a man-made source. We use a passive source. So it is a natural method, or based on natural source of energy that penetrate in the subsurface, and we measure the response out of this interaction. But all of these electric or electromagnetic methods, they have one major goal, namely to image the physical parameter of the subsurface, which is the electrical conductivity. So all of these methods are aiming at imaging the electrical conductivity of the subsurface. Now, talking about the electrical conductivity of the subsurface, as this chart is showing here, which is one of the textbook charts, showing how this electrical conductivity of the rocks span a wide range of value, from a few hundred of Siemens for the conductivity to a few 100,000 of ohm meter as a very resistive material. And please note here, so the conductivity is the inverse of resistivity or vice versa. So I may use resistivity or conductivity throughout the talk, but they are just the inverse of each other. It is good to know here and see that something like massive sulfides or graphite are super conductive material, while we have the middle range here like clay, mafic rocks, metamorphic rocks. If they are weathered or fractured and contain some material that increase the conductivity, they are in the middle range here. Whereas metamorphic rocks, unweathered rocks, they are super resistive rocks. Seawater and fresh water are in that range here of the resistivity values. And yeah, sorry. Yeah, The electrical conductivity of the rocks, when we are saying electrical conductivity of the rocks, we are referring to the bulk resistivity. In other words, it is the sum of the resistivity of the rock matrix plus the resistivity of the material which fills the pores and fractures inside the rocks. So, for example, high conductive rocks implies that it is cased by large interconnected network of pores or fractures which are filled with fluids, ores, melt, graphite, or sulfide. And this is what we usually measure and interested with. So there are several methods and ways to get, for example, from the electrical conductivity that we measure to porosity. This is something that can be estimated via Archie's law or other ways to get these parameters. Another thing that is to notice here is the graphite in the shear zones are stable over millions of years, and they are marker for all tectonic process. So by studying the electrical conductivity of the subsurface, we can reconstruct some tectonic process that happens millions of years. Yeah, as I mentioned before, MT is based on natural source electromagnetic waves, and basically these electromagnetic waves coming from the solar activity which interact with ionosphere of the Earth, creating ionospheric current system which penetrate in the subsurface, creating a secondary field, and that's what we measure. This kind of process is specifically for long period data. And also we have another source of natural EM waves is from the lightning. As you know, lightning is an electromagnetic waves, and this is usually considered for short period data when we measure electromagnetic or magnetotelluric data. Yeah, the whole MT method is based on the EM plane wave assumptions. That means the current system which is generated in the ionosphere propagates through the air and downwards and enter the subsurface. So it enters the subsurface at different frequencies. And once it starts penetrating the more conductive subsurface, I mean, in comparison to the air, the EM wave start to decay and namely exponentially. And this decay, the ratio how much or how this EM waves decay, depending on basically on two main factors, the subsurface electrical conductivity and the period of the induced field. And that's what we call skin depth. In other words, as this chart is showing here, for a long period data, as you can see here, the wave is start to propagate here in the subsurface and decays exponentially. And at some depth, when the energy of these waves decay to its 1 divided by E, equivalent to 35% from its initial value, then this is what we call the skin depth at which we can get information. Whereas for a little bit shorter period, the decay is shallower. And if it is a high frequency, of course, the decay is much shallower. So in few words, long period and or resistive subsurface casing a very deep penetration depth of the waves, and we can get information from very deep structure. Whereas short periods and conductive subsurface is the penetration depth is very shallow. Now, to visualize this phenomena or how the EM wave penetrate from the air down to the earth, I have here an animation showing, it is a simple animation showing how the electric field, the arrows of that showing the polarization state of the electric field as a function of time. So the colors here are red for high amplitude of the electric field. So we are not looking at the resistivity of the subsurface, the colors, but they are related to the amplitude of the electric field as a function of time. And the model itself, it contains a conductive background. Here, as you can see in that part here, we have a conductive block, and here we have a resistive block. At a certain period, at 10 seconds, you can easily see how the electric field or the decay of the electric field is at shallow depth. So the amplitude of the electric field is really very small at shallow depth. Whereas if we have a resistive background like this one here, you see that the energy is big enough and the penetration will be very deep in that case. Now this animation is just the electric field as a function of time. And now imagine that you have a sensors that you set up at the Earth's surface and you measure such kind of time variation, but not only for the electric field, but also for the magnetic field. So when we say sensors, they are nothing else than, let me see, yeah. They are nothing else than a pair of electric dipoles to measure the time variation of the electric field in two orthogonal directions. And for the magnetic fields, we usually use coils to measure also the X, Y, and Z component. So please note that the electric fields, the two components of the electric field are orthogonal, and also the other component of the magnetic field. And it is very important to ensure this orthogonality of the components, otherwise your measurement will not be correct. So you can rotate the whole system in any direction, okay, because later you can rotate the data to a specific coordinate system, but the most important point is to keep this component orthogonal. So this system will measure the time variation of the electric field and magnetic fields via electrodes and induction coils. At this point, I just want to say a few words about the data collection and data acquisition. It is that important as any other step later we use to image the electrical conductivity of the subsurface. In other words, controlling the data quality during the measurement and making sure that everything is correct will make sure that any step afterwards will be correct. If there are some problems with the sites, believe me, I mean, you will make life difficult later for the processing and for the modeling. Typical mistakes in that regard are, for example, the horizontal component are not orthogonal. Or if you are measuring the vertical component of the magnetic field, it is not vertical enough, or it is moving because it is not buried well. And also the coils are not well buried. And for example, wind will affect or vibrate the coils, the magnetic coils, and causing some noise on the measured data. So since we are measuring the time variation of the electric and magnetic field, at the end of the day, we will get time series of the 5 components of both electric and magnetic. So we will get the EX, EY, BX, BY, BZ. Some people don't measure BZ, especially in the industry. But as we will see later in some examples, how important is the vertical magnetic component. Anyway, so once you get the measured data from your sensors, there is a processing step here, which requires additional 2 or 3 talks to talk about it, but I'm not that expert in that process. But in a few words, inside this processing tools, what we are doing is going from the time domain to frequency domain, and to obtain something that we call an empty impedance tensor. So it is nothing else than a ratio between the electric field, the horizontal component of the electric field, and the horizontal component of the magnetic field. This impedance tensor here carries the information about the electrical conductivity of the subsurface. And as you can see here, all components in this equation are a function of period. So at each period, we will get some component like this one here, the impedance tensor. Another component that we can derive from these 5 electric and magnetic component is the so-called vertical magnetic transfer function, or TIPR. And TIPR is, as the name suggests, it shows you, or it tells you how much is the vertical component is tipped in the horizontal direction. And it is relating the vertical magnetic component to the horizontal component. And it's also as the impedance tensor as a function of the frequency. There are other parameters that are derived, for example, not directly from the time series, but are derived from the impedance tensor, what we call the phase tensor, which is also a function of frequency, real numbers, and you can imagine it as the phase of the complex parameter of the impedance tensor. Now, looking carefully or closely at this, the first component that we have, or first data type, the full impedance tensor, it has very nice properties that we will see it in a second. But people can use these values, these complex values, to directly interpret the data and look at the data, look at the quality, and make some interpretation. But most of people, they use the apparent resistivity and phase, which are derived directly from all components of the impedance tensor. So the apparent resistivity is nothing else than the absolute value of any of the component in the impedance tensor, multiplied by a factor here. And the phase is the module of that complex number, and by taking the arctangles of their imaginary to the real part. Now, this tensor has really very nice properties, and it can tell us a lot about the dimensionality of the subsurface. And it is the basic to analyze your data, to analyze the dimensionality of your data, to analyze the geological strikes or the electric strike in the data. For a simplest case, if you have a 1D model, so you have only 2 layers, row 1 and row 2. In that case, the impedance tensor is simplified by only 2 off-diagonal, which are equivalent. So the off-diagonal component. And the diagonal component zxx and zyy are 0, because there are no variations in any other direction rather than in a z direction. Now imagine that your subsurface has some intrusion, like a dike or something that is different in terms of conductivity from the first and the second layer, and it has a limited dimension in y direction, for example, and also it is cut in a z direction. In that case, we still have the diagonal component of the impedance tensor are zeros, but in that 2D case, the off-diagonal component are unequal. So they are not the same as in 1D case. In a 3D case, of course, I mean, if you have an object that has a limited dimension in all directions, in that case, the impedance tensor is full occupied and all components are unequal, which gives you an idea. I mean, by analyzing the impedance tensor, which is a very important step toward the modeling or interpretation, is to analyze your data and tell a little bit about the dimensionality, what you can see in the data, which is very important step before doing any kind of interpretation or modeling of the data. The other component, TIPR data, as I said, it is a complex number again, and it's a function of period, and usually it is visualized in terms of induction vectors. So you can derive the induction or the length of that vectors by taking the square root of both components, and the phase or the rotation of these vectors by taking the arctangles of the real to imaginary part of the 2 components. These data types are really very important, and they can tell you a little bit about the subsurface without doing any kind of modeling of the data. And we will see some real examples and show the value of that induction vectors. But to simplify the things here, imagine that you have, this is a map view, this cartoon here showing a map view of a resistive background, row 1, and we have a conductive anomaly that is elongated in southwest northeast direction, and you have a couple of empty sites. So if you measure the vertical component, then you will see and present them as induction vectors. You will see that such kind of vectors, they point towards, toward the conductive anomaly. In the physical context, they are pointing to high concentration of the electric current. In that case, inside the conductive materials. Directly above the conductive material, the vectors go to 0. The length of them goes to 0, and close to the contrast, the vectors are very long, and away from that contrast, they start to go to 0 again. So they give really a good overview on the data and what we are expecting in the subsurface. I will show really a very nice example on the induction vectors. Yeah, that was the quick introduction on MT and what we are expecting or what we are using in order to interpret our MT data. And I will start with you the journey over the world to show some examples from continental scale applications to understand the lower crust and uppermost mantle, specifically the lithosphere-astenospheric boundaries, using the magnetotelluric methods. We will start from one of the largest MT array located in the United States. It's called the US array. And it is part of an EarthScope, which is a national geoscientific project aiming at exploring the North American tectonic plate. And the US array, or US transportable array, is part of that project, and it contains data something like seismic, GPS, and also magnetotelluric. All of information can be found on that link here, earthscope.org. And for the MT array, as you can see here, I mean, on that scale of exploration, we are interested in a deep structure, so long period MT data are collected. So measuring time is around 3 to 4 weeks. The time series are measured. In that case, you will get periods above 1 second to around 20,000 seconds. The site spacing for this array is around 75 kilometers. And up to date, I've just downloaded yesterday the last set of the data. There are around 1,100 LMT sites. And all of them, for those who are not familiar with this array, all of these data are available to download. So you can download them from one of the links that I have here on this slide. Now, the distribution of the MT array, it is as shown here. So almost the northern part of the United States is covered with long period MT data. The portal where this EDI file exists, it includes also some small or local arrays like the one here located at the western coast of the United States. But I will consider also only the long period of the US array in the next slides. There are several publications using this data, and for example, in the western part, I was honored to work with this data back in 2014, and we published a paper using this part here. Later, there were other scientists who used the data and published also publications, 3D models from all of these data sets. Recently, our colleague Egbert collected all of these models and put them in one 3D models to give an overview on the northern part or the electrical conductivity of the northern part of the United States. So in the next few slides, I will talk about the publication that we have did on that part here in northwestern United States, and consider only that model here. And this figure here shows you the basic tectonic and the location map of the empty array used in that study. And it is very important to know, sorry for that. It is important to know what is the tectonic condition in northwestern United States, because it is a key observation for our interpretation later. So basically, as many of you know, we have on the oh my God. We have on the western part the subduction system that is consisting of Juan de Fuca plate, Gorda plate. They are subducting below the North American tectonic plate. In between, we have the basin and range, which is part of the so-called extensional regime. Farther to the east, we have the cratonic area. So there are not a lot of tectonic activities in that part. And it is considered to be one of the stable part of the lithosphere. Now, keeping this picture in mind, I mean, this kind of tectonic system, the three groups here, and looking at one of the cross sections derived or extracted from the 3D model we have run over all the data here in that part. And we are extracting only one cross section that goes from west to east. It is very interesting to see that such kind of conductive anomaly, it goes, by the way, down to 400 kilometers. And another observation here, or other notes to tell, is that in all the figures that I will show, red and yellow colors are for conductive anomalies or conductive structures. Light blue to dark blue are resistive structures. So as you can see here, we have the subducted plate here of Gorda, and looking at the upper part of this conductive or this resistive anomaly, it is correlate where we have the line, the dashed line, which is derived from seismic data. Also, the white dashed line here shows the position of the MOHO. And the most interesting feature also to see is this dashed thick black line that shows the position of the the lithosphere asthenosphere boundary, LAP. Okay, and as you can see here, it is really nice correlating with what we have in the eastern part of the study area. With regard the Wyoming craton, which is a very resistive block located in that part of the model. And you can see here that it is correlate with the location of the lithosphere asthenosphere boundary. In the central part where we have the extensional regime, you have the Snake River plain that goes toward the Yellowstone supervolcanoes, which is located somewhere here on the map. Let me point that here. Here, what the location of the Yellowstone volcano. And as you can see, we observe a high conductive material at the lower, at the base of the crust. And below that, we didn't see any resistive, implying that the lithosphere here is very thin. But at the greater depth, for example, below 200 kilometers, we start to observe some conductive anomalies. And our interpretation for that, it is the asthenosphere or the electrical asthenosphere. Yeah, this is a 3D view of the model, just to give you an idea how is the model looks like. If we extracted the upper 100 kilometers of the model and present only isosurface related to resistive materials, like this one, it is on the screen now, and it is related to the oceanic lithosphere that is subducting below the North American tectonic plate. And due to this subduction, you see that we observe conductive anomalies, and in the back arc, and we interpreted that as an upwelling of asthenosphere in that part of the model. We also observed several conductive anomalies like this one here coming, or it is embedded between two other resistive structures, and our interpretation for that is setters. And you can clearly see here, if I stop for a second here, you can clearly see the resistive material of the cryptonic area. And as I said before, that the eastern part of the study area is characterized by stable tectonic plates. And this is what we can image in the conductivity model, a resistive blocks. It's also nice to observe here, if you can see my pointer, this conductive anomaly that coming from the asthenosphere or from deep structure, conductive structure, it is going toward the Yellowstone. And there are several publications on that, I mean, in terms of seismic, and correlate to great extent with our model here and the interpretation that we did. Yeah, the next stop in our journey is in Africa, South Africa, and namely talking about SAMTEX array. And for those who are not familiar with that, it is a South African MT experiment, the same as US array. It aims at exploring the South African tectonic plate. But this data set has a different period range, long period MT data, broadband MT data, and AMT data. And it is not only to explore the deep structure of the subsurface, but also has some implication on the mineral exploration activities in South Africa. So there are many publications and contributions using this data, and you can find the data. They are publicly available data. You can find them on MTNet as well as a list of publications. For the talk today, I will only concentrate or focus on a study published by our colleague David Hoza back in 2013, and he took a group of the sites located in northwestern part of the array. So David took this subset of the data and start exploring the subsurface in terms of electrical conductivity, and he started by a 2D inversion on some transects along these profiles here, for example. The top one showing that one in the western part, and it goes farther to the east. The most interesting observation here is from the 2D modeling is a very conductive anomaly located where the Damara belt, it is located in that part here. And directly to the north of it, somewhere here, the 2D model shows a very resistive block, similar to what we saw in the US array. This cryptonic lithospheric structure are really very resistive. Okay, and the same observation can be seen here also in that array, and that's this resistive block that extend to around 120 kilometers. The same observation, if you take a look at the section located here, you can still see the conductive anomaly in the lower crust, I would say, and also this resistive block that are related to some cryptonic lithosphere. So the main observation is that the footprint of cryptonic resistive block of Angola and Congo, as well as the Damara belt, observed as a conductive anomaly in this modeling experiment. David also did some efforts to do 3D inversions, but keep in mind, I mean, the spatial distribution of this array is not that appropriate to do some 3D inversion, but he did a good job in order to get a sophisticated 3D models. And the main observation here, again, we have, if we look at a map view at a depth of around 20 kilometers, You can see that the model shows that we have some conductive anomalies located in the Mara belt, and all of these resistive blocks are related to the lithospheric cratons that are distributed in the study area. Yeah, these are all from David Khuzam back 2013. Now moving further to the east, and we will consider the AusLAMP, which is another continental scale empty array. And the major goal is, of course, to reconstruct the tectonic evaluation of the Australian continent. And as you can see here on that map, the distribution of the empty sites. The black ones are in planning. The red purple points or circles are for the data that are collected. And there are several publications on the collected data. The nice thing in this array and this national project is that the researchers from Australia and other parts of the world, they are trying to make a connection between what is happening in the lower crust with mineral system that is observed near the surface. So they are trying to attach the deep process with a shallow process. And that has an implication on potential minerals and energy resources for the future. If you look at the publication, I personally recommend you the most recent one, Robertson et al., Kate Robertson et al., published early this year. And the nice thing is, beside discussing the structure in Australia, the electrical conductivity structure in Australia, is also she discussed how to go with the data in 3D. It is a very interesting publication. I recommend you to see it. I personally got the whole slide from Kate, and the hope to show you what is the value of the magnetotelluric on such kind of large scale, of course, and the connection to mineral system. So, for example, this conductivity model is extracted at 30 kilometers from a 3D models. And again, we see these resistive blocks are cratonic areas. And in between, we have these kind of conductive stripes that are located and bending in some ways in the model. The most interesting observation here is these green dots here. They show the location of where the copper occurs in this on the surface. And it is correlate very well where we have this contrast between resistive and conductive anomalies in the 3D model. For example, here you can see very nice where these or the correlation between the occurrence of copper and the contrast between resistive and conductive anomaly, and many other places here. Yeah, we cannot go, I mean, since we are in the eastern part of the world, we cannot leave without talking about SINOPROBE, which is another continental scale empty array, also aiming at exploring the northern part of China. And up to now, there exists around 700 broadband empty data and 70 long period empty data. The sites are distributed on 1 × 1 degree of latitude, longitude, and this map here showing the distribution of the broadband data, the triangles, and the red squares are for the long period data. It is also a semi-continental scale, and there are some results early published by Haodong et al. In 2014. And here I'm showing some of the results obtained in this study. Beside the map views that you can see it on the left-hand side at several depths. The most interesting part here, if we look at the sections, that goes to around 150 kilometers, we see some conductive anomaly that is coming from the lower part of the model and moving up, and at the crustal level, they start to spread in the horizontal direction. The same observation is also, or the same structure more or less are observed also in the other direction in south-north profile here. And it seems like it is an unstable feature in the 3D model. To justify such kind of structure, I mean, of course, you cannot drill to that depth, but the main methods that we usually have is to compare our results with other geophysical or geological information that we have in our study area. Now, knowing that the upper part here in this figure is the shear wave velocity, and the lower part is the south-northern profile I've showed in the previous slide. Now, knowing that the shear wave velocity decreases in the presence of fluid, it is easy to interpret such kind of conductive anomaly as an upwelling of mantle fluids that is upwelling in that part of the study area. And what I want to see here is a nice correlation between decreasing of the shear velocity here and increased conductivity in that part. And this is a sign of mantle fluids that is upwelling. Also, if you look at this, if you look at this high velocity here in the S-wave velocity images, it is correlate where we have the resistive material. It is also maybe a cretonic part here, which is very fast in the seismic and very resistive in empty or electrical conductivity. Now, going a little bit shallower and considering crustal studies, in my understanding, I mean, there exist hundreds, if not thousands, of excellent publications on crustal and near surface studies using MT. I found this very interesting chart published on MTNet, prepared by Alan Jones, and it shows these publications between 1960 to 2020. And the most interesting part here is to see how the publication or the use of MT is increasing in the last couple of years. And it looks like an exponential increasing of publication, showing that the MT methods is becoming much more popular and much more useful for many applications. This kind of course, this kind of increasing of use of MT is attributed to a rapid development in instrumentation, stable processing codes, as well as modeling codes. So all of these components are attributed to this rapid or exponential increasing of the MT use in the geoscience community. Now, as I said, I will talk about the crustal studies, and I will go back home in Jordan, where I was when I was doing my PhD. I was honored to work with the GFZ group in a project funded by the Deutsche or the German Science Foundation. And the project was to understand and explore the Dead Sea transform, exactly where we have the Dead Sea basin here. And why we are interested in that part of the world is because we have the Arabian plate, the tectonic plate at the eastern part, and we have the Sinai plate, and in between them, as you know, we have the Dead Sea transform, which is one of the largest or longest strike slip transform fault in the world. At this point at this point of or at this location of the Dead Sea transform, and because it has an opening component, this opening component created the largest pull apart in the world. And this is what we call the Dead Sea basin, as you can see here. So our main interest is to know what is the electrical conductivity structure in that part of the world. For that, we have collected in around 150 MT sites, including broadband and LMT sites, mainly along an east-west profile, but we do have a shorter profile here for later, a 3D inversion extending in south-north direction. So as any other publications, we start exploring the data by running a 2D inversion. And this is the our preferred model overlaid with all kind of information related to that study area. And as you can see here, our story is correlated very well with the available geodynamic, geophysical, and geological information from the study area. The most important observation in this 2D model is that conductive anomaly that is located between the two resistive blocks here. Another nice observation is to see the implication of the Dead Sea transform, which is, if you can see my pointer here, on the service trace of the transform is located here. And if you extend that, the effect of the fault toward the depth, you see it is located exactly where we have the transition between the resistive block at the eastern bar toward the conductive anomalies in the center, and in the other part we have the resistive basement again. So the whole Boulevard Basin is located in that part here, and the deep structures showing the conductive anomalies. And our interpretation is a mantle-derived fluid that is interacting in the structure in that part. Interacting in that part here with the rocks, creating some geological or some rocks here, muscophytes, and the rest of the fluids is penetrating upwards. So the story that we have created based on the conductivity model and also the geological and other information are consistent with the tectonic state of the Dead Sea Basin. Since we do have also a shorter profile in north-south direction, we decided to do a 3D inversion. But again, as the situation with David Hosa in northwestern part of the SAMTEX array, the spatial distribution is limited and making the 3D inversion to some extent difficult in such kind of scenarios. But nonetheless, I mean, looking at the 3D features that are observed here, for example, if you look at this resistive block here, it is consistent with what we call Alisand salt diapir, which is also observed in boreholes. Farther to the south, in that part here, we observed a very conductive anomaly that goes down to around 12 kilometers. And this kind of formations saturated with saline water, making this structure very conductive. And such kind of picture is consistent with also geological and other geophysical information. Nonetheless, I mean, toward the depth, it was not that easy to get more information, again, based on the spatial distribution of the sites. Local application upper crustal studies, and here I'm referring to geothermal and mineral exploration in which we use the magnetotelluric methods. And the first example we have, is for geothermal exploration using MT, and this model here, or this section derived or extracted from the 3D model, is kindly provided by a company in Turkey, Energeo Camellia, and they allowed us to show this nice example. What you are looking at, again, a conductive anomaly observed in the 3D model, and there will exist a borehole. And if you correlate the clay stone, which is in the stratigraphic column of the borehole, with the location of this conductive anomaly, you will see a very nice correlation between the two. In total, In total, there were 300 empty sites. They all modeled using our web application that includes the ModEM code. And that was one of the successful stories we have got in geothermal explorations. And based on the 3D conductivity model obtained in this study, the company went and drilled several production holes. Another example that I found the data, publicly available data for geothermal exploration is located in Idaho or southern Idaho at the border between Idaho and Utah in the United States. And it is the so-called Raft River geothermal area. There exist 105 broadband empty data. As I said, they are publicly available. And when I downloaded this data, I thought they are maybe synthetic data because they have really high quality data. And as we will see in a second, for example, looking at the raw data as induction vectors, you can do your first interpretation without doing any kind of modeling. So this is the location map of this local array for geothermal exploration. And here is the induction vectors presented at different periods. And for your reference, and as a reminder, when I was talking about the induction vectors, if you have a conductive anomaly in the middle of your survey area, how is the behavior of the induction vectors? This is a cratonic presentation, while here, this is from real world data. So as you can see here, at long period, they point toward the east. And at a shorter period, they start pointing to something in the center part of the array. If you can see my pointer, just keep looking at this part here, and you will see that all the induction vectors in that part, they are pointing to that way. And in northwestern part, they are pointing to the center. This gives you an indication that at a certain depth, you are expecting some conductive anomaly running in that part here. And at deeper sections, you will expect to see some conductive anomaly located to the east. Now, running an inversion on this data, a 3D inversion on this data, again, I'm showing here on the top right section at a depth of around 1 kilometer. And as you can see here, this conductive anomaly is well imaged as what we see in the induction vectors. And toward the eastern part, we start to see the top of a deeper conductive anomaly. And this is consistent with the behavior of the induction vectors that at long period, there exists some conductive anomaly here. Now looking at the section that is from A to A prime, here and present the electrical conductivity along this section, you will see how nice is this conductive anomaly is located, and the basement, which is much more resistive in that part. And keep in mind, forget to mention here that this study area is located in the basin and range, and it is closed. If I go back quickly to, sorry, okay. If I go back quickly to that, to the location map, how to escape now here, okay. I can't go. I can't go back.
I have no idea. Oh, did that work? Is that going forward?
Yeah, it's going forward. I want to go back for a second. I just want to disable now. Okay.
Okay.
Okay, now, just a few words on the location that I forget to mention here, that this study area is located in the basin and range. And if you still remember from the US array, that this is an extensional area here where a lot of conductive anomalies are observed in the lower crust. And it seems like such kind of geothermal activities are located or correlated and connected to something very deep. And also for your information, in that part here is the Yellowstone. Now, going further now with the 3D model, again, I mean, we obtained a very nice 3D electrical conductivity model from this study area. And of course, the electrical conductivity alone it tells you something about the subsurface, but it will be much better if correlating the data with other geophysical and geological information. In that section here at the upper right corner, I am showing a cross section, the electrical conductivity section, and at the top you see the magnetic anomaly, where we have a high magnetic anomaly in that part, and it goes to low magnetic anomaly. Another observation here is that there is a fault that is obtained from gravity data, and as you can see here, it is located. If I activated the pointer here, yes, this arrow here shows the position of the service trace of a fault obtained from gravity data. Now, if you extend that the location here with depth, you will see that this dashed white line correlate very well with the position here, and also the transition from the basement, which is resistive here, to more conductive anomaly in that part. Another, I mean, we still didn't completely interpret this data, but as you can see, there is another tiny magnetic anomaly, and maybe it is related to that contrast also at greater depth. On that section here is, I've also extracted one of these, a section from the 3D conductivity model, and overlaid with an old seismic interpretation. And as you can see here, there are a good correlation between many interfaces obtained from the seismic as well as the conductive anomaly in that at this part at this shell or at this part of the model. The point here is that comparing the conductivity model with other geophysical and or geological information is very important in order to validate the meaning or give the geological interpretation of the conductivity model. Now, another example for it is also related to shallow studies is for mineral exploration, and namely it is a very large array located in Australia, Queensland, and specifically in Cloncurry field, and it consists of 400 broadband sites. I was also honored to work with this array here in order to get a 3D conductivity model. What we are looking at the moment is the geological units derived from a 3D geological model. And this movie will show you how is these geological units correlate very well with our 3D conductivity model. So if I run the movie, this geological information or map will disappear and showing the electrical conductivity in the model. Just a second. Now we are looking at the electrical conductivity at a depth of around 1.2 kilometers. And as you can see, this kind of contrast or these interfaces in the geological model correlate very well with the location of the conductive anomaly. Now looking at the southwest northeast section, we observe very conductive anomaly located in the upper crust, and it is going toward the mining area in the study area here. This is the mining area where the green triangles, and you see that there is some conductive anomaly coming from the crust at the crustal level, something below 5 kilometers. And we decided, I mean, based on this study here, we decided to take a subset of the data and modify our modeling process in terms of using very fine grid and making a smaller sized model. And that's what we got if we run the 3D inversion on a subset of the data with high resolution grading. What I'm showing here again is a cross section located or extending from southwest to northeast. At the top, we see the magnetic anomaly. And as you can see here, there is a huge conductive anomaly located exactly where the mining area is located. And if you still remember, I mean, from the same study area, we observed that large conductive anomaly that is coming from around 10 kilometers. Here, keep in mind, I mean, I'm not using the full period range, so I'm interested in the upper 2 to 3 kilometers, and the deeper part is not well imaged. Whereas when using the full period range from this data, we observed that conductive anomaly that is located somewhere here. And the point is that such kind of magnetic anomaly might correlate very well with the conductive anomaly that we have in our 3D model. Beside that, we observed some conductive anomalies where we have these magnetic anomalies in the magnetic maps, and they are really correlate very well with these two blobs in the electrical conductivity model. Yeah, I mean, I am almost done with the showing some examples at various scales, at various depths. If you want to see more examples, you can find them on any of these websites, and feel free to send me an email if you have some questions or comments. So there is my email address at the bottom of the slide. You can write me anytime. So to conclude, I mean, the magnetotelluric method is really a powerful method for imaging electrical conductivity of the subsurface at various depth levels, from the uppermost mantle to uppermost crust. The several continental scale magnetotelluric arrays, they are collected from several places in the world. They allow us to better understanding the deep structure of the Earth. And as I mentioned when I was talking about the chart of the MT publication, it is such kind of rapid increasing of the use of MT is attributed to rapid development, instrumentation, processing, and modeling code, either in 2D and 3D. Also for 3D, the availability of computational resources that makes the 3D interpretation and modeling very easy. All of these together making the MT as a standard method in many geothermal and mineral exploration around the world. Last but not least, I will leave you with that a 3D movie from the Cologne mineral area. And here I'm showing just isosurface from the conductive anomalies, together with the gray surface here that are obtained from the 3D geological model. I just want to show you how nice is the correlation between the interfaces from the geology with the conductive anomaly. And for the depth reference, I mean, this slide here in the background is at around 7 kilometers. And keep in mind, I mean, these models that obtained from MT data is derived from the data. So there are no constraints in the model. We started the inversion from homogeneous subspace. We don't know anything about the subsurface. And that's what you can get if you invert the data. Very nice correlation between geology and the electrical conductivity distribution. Also, this conductive anomaly that is coming from the deeper part and ending toward the mining area. And as we saw in the magnetic anomaly, it is correlated with high magnetic anomaly. At this point, thank you very much for your attention. And yeah, if you have any question, either write it here or, as Stephanie said, you can write it and chat later on that. Thank you very much.
Thanks very much, Dr. Naser. That was a great talk. I think we're going to make every geophysics honors student at WITS watch your talk. It was very useful to have the theory and such good practical examples. I've got several questions. I just would like to also compliment you. I don't think we've ever had a brave enough presenter that would have so many videos and that they actually worked. Most people are far too scared. You were very brave. I was impressed. I'm just scrolling up here. So the first question is from Sue Webb. She's one of my colleagues at WITS. She said, have you looked at the MT results with seismic and anisotropy to relate mantle flow / mantle fluids with links to large scale crustal structure and mineralization related to fluids? Did you get that? I can read it again. Was it fine?
Myself, I personally didn't do that, but I'm pretty sure that there are many studies that they are doing such kind of analysis, for sure. I mean, I'm not familiar with that kind of correlations, but I'm pretty sure I've read several publications on such kind of correlation.
Okay, thank you. I've got a post from Anonymous. Just to let everyone know, there's been a few questions about how do you change your name on Microsoft Teams so you're not anonymous. I can't remember. I know I figured it out before, so I will let you know.
Is it
so Anonymous,
for you or for you?
Yeah, do you know? So the question is, the large studies over continental scale are a fantastic example of a mineral systems approach to exploration. Obviously, the USA, Canada, Australia, China, as single continental-sized countries have led the way. Are there more plans for more multi-jurisdictional, in brackets, multi-country studies in Africa that you know of? I would hate to deal with the logistics of that.
So is the question at the end of the question, is there some efforts to do larger scale in Africa, for example, or is that?
Know of any in Africa that are being planned across countries?
I mean, aside from SAMTEX, maybe Alan Jones in his talk will talk more about that part. But as far as I know, there's no extension for SAMTEX to go further to the north or field. There are, of course, several efforts to fill the gaps in that array as in SAMTEX array, and it is also for mineral exploration purposes. But as far as I know, I mean, there are no programs to go further to the north and extend the SAMTEX, for example, further in Northern Africa, or even in the Middle East or in other parts of the world. There were some attempts to do something here in Europe, but as far as I know, it didn't come through also such kind of large or continental scale arrays.
I think money is tight. We've got to get the companies on board. So Eric Steele from Australia says, very interesting and enjoyable talk. Thank you. ZTEM is effectively an airborne variant of MT, making use of the Schumann resonance and measurement coils, in brackets, both ground and airborne based. Can you deliver comment on the effectiveness of the ZTEM for mapping relative shallow structures when compared to that of MT?
Yes. I mean, ZTEM is, as it's said, it is very powerful also methods, very rapid, and it is to 90% similar to TIPPER. So this kind of horizontal contrast, you can map them very easy using ZTEM data. And we do have good experience working with this ZTEM data for mineral exploration purposes also. And they provided really a good correlation with surface geology, and it is for mineralization was a good example. Of course, there are several studies. I mean, if you want to go deeper, as if you want to know the source of such kind of mineralization, I mean, you have to keep in mind ZTEM doesn't have that deep penetration depth. So in order to make benefit of both ZTEM and to go deep, you need to collect some empty sites, ground-based empty sites, in order to combine both in a 3D inversion so that you can get shallow structure as well as deep structures.
Great, thank you. I've got 3 more questions, but I just wanted to say something before anybody logged out. I've just posted now a link to a Google Hangout for people if you want to socialize after the talk. So you'll see it. I've just posted in the Q&A. So you can click there and go there, but we still have 3 questions. So please wait. It was just in case people were trying to head away. So the third last question from Joel at Anglo. He said, is there any theory of what is the cause of the very low resistivity anomalies at depth? He said they look like the conductivity was that of seawater. I asked him where he saw this, and he said there's one under Olympic Dam in Australia, there was one on the Dead Sea slide, and then he said there seems to be one on every slide, and he saw one on the US in the US asthenosphere under the stable Craton, and another one under Ernst Henry. So do you know what he's talking about?
Yeah, I mean, this is asthenospheric materials that is upwelling in the crust. I mean, these are magmatic fluids, and that is upwelling from the asthenosphere. And you can see them in many places in the world, especially at this kind of tectonic, where the tectonic is active. You can see a lot of such kind of upwelling. I mean, we saw that also in China. We saw that in Australia and in the United States and many places. I mean, these deep conductive anomaly are observed in many of these large-scale MT arrays.
Great, wonderful. The next question was from Mohammed. I was just trying to find your affiliation. It was someone from Iran at the Shahrud University of Technology. So, but now I have to scroll down and find his question. That's the problem with this Q&A. Hold on. And he said, is it possible to use MT for small-scale exploration? If yes, how? This sounds like it could be another talk in and of itself.
Yeah, but what is the definition of a small? I mean, you can go, I mean, 100 meter times 100 meters. I've got a discussion with a guy from Australia who they are planning to do on that scale. I mean, 100 station separation, 100 times 100. Of course, you can do it, but in that case, I mean, you need to consider audio magnetotelluric with high frequency and interested only in the upper, let us say, a few hundreds meters, not deeper than this. Of course, but you can do it, definitely.
Okay, we've had just two quick questions that link with your previous one. I think Joel was saying ZTEM is not MT because it doesn't include electrical field measurements, but I think we were saying they're similar. So yes, we hear you, Joel. And then the next question was, do you have an example of both ZTEM, shallow and details, and MT, deeper information? Do you have any of those examples? Not that we have time to look at it now.
I have only an example which I can show. I mean, I have a few examples, but I cannot show it because they are confidential. But I can quickly show an example that shows a correlation. I hope that I can find it quickly. Shows a correlation between ZTEM and IB measurement. Just a second, please. I hope that I can find it quickly. Yes, it is there. And I will share my screen if you don't mind, Stephanie.
Sure. I think you've just got to share a second time because currently you're sharing PowerPoint. There we are. So
I stopped sharing now. Okay.
Yeah, and do it again and then select the new window or select your desktop. And so if you click on the share button.
Yes. Just a second, please. Okay. Just to find that section, because as I said, I mean, this is the only example that I can show here using the ZTEM.
It hasn't come through yet. Have you clicked share?
No, I still didn't click on share. I just want to find the figure before I...
there you are. Okay, I will... Oh, it's disappeared. Your screen was at the bottom for me to click on, but now it's gone.
Did you see now my screen? No.
It came up and then it disappeared.
I see. Okay, let me try it again. Now, I guess you can see it. No, it kicks me out.
Yeah. I'm not sure why. Do you want to try one more time and then?
Yeah, okay.
Maybe try share your desktop.
Okay, then maybe it's
the application.
Okay. Maybe it's a good idea. Desktop, where is that? Okay, desktop. Yes, found it. Okay. Can you see now my screen?
I can. Let's hope it doesn't push you off. I can see also my video at the bottom if you want to minimize that. Although I'm sure everyone enjoys seeing me.
Okay. Okay, I hope that you can see this figure here. I mean, this is a cross section. And the top left corner, you see the location of that array. I mean, this is ZTEM data. Okay, so there are thousands of points at, I guess in that array, there were around 5 periods or something like this. But anyway, the point is that we inverted this data in 3D, and this is what we got from the 3D inversion of ZTEM data. And this dashed line shows the flying lines. And to make or to justify our model, we compare it with an IB section existing in the same location. And the point we are trying to make here is the correlation between chargeability observed in the IB with such kind of conductive anomaly that we have here. For example, D2 is comparable in both in IB and chargeability. We will be able also to trace this D3 conductive anomaly and also further to the right of the section at greater depth or at the depth of minus 800 meters, we can see that conductive anomaly here and the chargeability. I mean, combining MT, of course, combining MT and ZTEM, I have some studies, but seriously, I cannot show any of them because they are confidential.
Great. Thanks for showing us that and at least being able to show us one slide. I think our closing question comes from Oleg, who I forgot was actually the one who did organize you for this talk. He said, ModEM is a very useful and effective code for MT data interpretation. What new developments are you working on with ModEM? If you can tell us.
Sorry, I wasn't, sorry, could you please repeat the question?
No problem. So he just asked, Oleg asked, what new developments are you working on with ModEM?
Yes, yes, in ModEM, I mean, it is an ongoing development process in ModEM. And at the moment, we have implemented, for example, as I was showing in a second, the ZTEM component or CSEM component, or I mean, the development also on accelerating the solution. Right now, we came up with a version of ModEM that is at least 3 times faster than the previous version. Beside this optimization and accelerating the code itself, we are working on another mathematical approaches in order to solve the induction problems in a different ways.
Well, that will keep you busy for a while. Thanks to Alan Jones and Joel. They've shared 2 references that are posted in the Q&A that you can take a look at about joint version of ZTEM and MT data. But I think let's call it quits there. Thank you so much for your time, Dr. Naser. I would hand over to you a bottle of wine, but we will...
Maybe even if we are face to face, I will not drink.
No, oh, that's a good point. I will have to send you some like e-currency that you can go buy, take yourself out to a restaurant. But thank you for all of your effort and your time. If you'd like to also come along to the Google Hangout, I'm sure people would like to speak to you on a more informal basis.
I will click on Hangout and get in touch with, hopefully with some people who will be around there.
Wonderful. So everyone can see it in the Q&A. Please click there and have a wonderful weekend. Everyone, please stay safe.
Both to you and to everybody. Thank you very much.
Thanks. Have a good evening. Thanks, everyone, for joining us. This talk will be up within the week on YouTube, and we'll see you on Google Hangout. Okay.
Bye-bye. Thank you.